Now we want to listen to Professor Ming. Hello. We want to listen to Professor Ming Zhang from the Department of Computer Science, Peking University, Beijing, China. Our professor, our able, eminent professor, is the head of the Digital Libraries Research Group in Peking University. And she is my mentor. She is here instrumental to my progress and development in the field of computing. She'll be speaking to us today on graph representation learning for drug discovery. So listen to our dear prof as she explains, as she speaks to us. Thank you.
Okay, thank you. Can I share my my screen? I think that somebody, somebody is sharing the screen. So, yeah, close. Okay, I'll try. Where's my? What's the problem?
Let me
try. Yeah, I'm not sure, but I'll try again. I'll try to open my BIOS. Oh no. Oh. Yes. Yeah. I think it's here. Okay.
No, yeah.
Can you so is it can you see my
Yes, we can.
Oh,
we can now.
Okay. Thank you. Thank you, Bonani, for the invitation, and thank you all listeners and the colleagues. I would like to introduce our recent work, research on graph representation learning for drug discovery. Actually, I'll introduce two papers. One is a clear paper to 2020, and the other one is ICML 2020 paper. So we know that CNN is typically for fixed size image grids, and RNN or vector vector is for text and sequential data. But for graph, the graph representation learning is very hard because it's much more complicated. And you can see that the graphs have complex topographical structure and no fixed node ordering or reference point. So, and also it's dynamic, and the graph data have some multimodal features. In my group, one of my former PhD student, Jian Tang, he's now a professor at Mila, Montreal University. He published two papers and proposed two models. One is line at triple W 2015. This paper is the most cited paper in recent 5 years for triple W conference. Now we have more than 2,700 citations. And the other one is on large ways. It's published in W 2016. So we have very efficient graph representation learning model. So it's kind of a large information network embedding. So it's kind of embedding. And nowadays, we know that GPT-3 is a very good generation model for NLP, and it can do a lot of amazing things. That's very creative, and we know that also GLOW for image generation, it become better and better. Nowadays, it's almost we cannot. This is totally created by computer, but it's really like a true picture, true human face. So to the drug discovery, we generate some new drugs automatically, and so we can save time and also save money. We know that typically for a new drug discovery, or we typically we need more than 10 years. We know that nowadays the whole world is suffering from by the COVID-19, and the vaccine. You know, the vaccine is very important for us, and also some cure medicine is are very important for us. Nowadays, actually, we don't have cure for COVID-19. People mostly recover by themselves. Nowadays, many machine learning models or machine learning algorithms are developed in this area, in drug discovery area. We can see from a paper, this is chemical shifts in molecular solids by machine learning. This is published in Nature Communication, and it announced that the AI model is 10,000 times faster than existing methods. Now, I'll introduce two papers just recently published and proposed. The models are proposed by my student. So, but we can see that typically for the drug discovery, the first one is molecular generation. So we need to generate some structure of a molecular, and then we if we announce that this is a new drug, but how can we composite this drug? So how to make this drug? So the second task is ritual synthesis prediction. So we can tell the chemists how to produce this kind of drug. And then also we have other tasks such as optimization, and also side effect test, and so on. But first of all, my group are working on task 1 and task 2. For task 1, the molecular generation, we want to generating realistic, novel, and unique molecules and design with desired property. So we need to test some drug likeness, octanol water partition, core efficient, and so on. There are a lot of existing research right now for drug discovery. Because of the time limitation, I won't introduce them one by one, but we can know that some of them, for example, VAE-based models, they are with low bound evidence and some gain plus reinforcement learning models. They are unstable. The training and the training parts are unstable. And for flow-based, the flow-based ones, most recent models, but this kind of models are also unstable. We need to so we need to propose new models and to conquer this kind of weakness. So this is the structure of the proposed model of our ICLEA 2020 paper. So the key idea is to decompose the generation of a molecule into a sequence under a specific order, and then we use an auto-regressive flow to model the sequence. So this is the structure of the or the illustration of the model graph AF. Actually, we train this model with reinforcement learning. So you know that for the molecular structure, we can see these structures as subgraphs. So we can use the reinforcement learning and so the state is the current subgraph, and the policy is auto-regressive flow to generate node age based on current subgraphs, and we have the reward. This is intermediate reward, and also we have some final reward. So the experiment we can see from this table that we can see that graph if archives competitive results on all metrics, on all the metrics. So that's for validity, uniqueness, and novelty mostly. And also we have some restriction on this metric. And this one is we can show that the property optimization, we compare of the top 3 property scores of generated molecules. We can see that for both personalized log P and QED, our proposed model graph AF outperformed all the baselines. Also, this one we can see that for the constrained property optimization, we can see that comparing with the baselines, graph AF significantly outperforms all previous approaches, and almost always succeed in improving the target property. We can see the visualization. We can see that the structures produced by graph AF our model, and it's very similar as just very like two drugs in the part. And then I'll introduce the second task, which is synthesis prediction. Actually, this is the way we tell the chemists how to produce the drug we generated. So this is the left side is the product, given the product which is generated by our model graph AF, and then we need to predict the reactants, and we need to tell the chemist how to produce this kind of product. There are some related work. First of all, of course, we have template-based research or template-based method. We can see that this kind of methods, they have some limitations. Mostly, the first of all is that the poor generalization on thin structure, and so if we don't know the structure, we don't have this kind of structure before, so we will never generate this kind of a new structure. So only because of the follow the existed template, so it's not easy to discover new structure, and then it requires subgraph isomorphism, which is a very computationally expensive. So and then it requires some domain knowledge to extract or design templates. So we need a lot of experts to extract or design templates for us. This is also very expensive. The second kind of related work is sequence-to-sequence based models or methods. We know that there is a very famous format is called SMILE. So for the SMILE, it's kind of sequence, just like sequence consists of ASCII text. And for this kind of method, they also have some limitations. Because SMILE itself only can represent sequential order, but actually molecules, this kind of a structure, the structures are graph based, or it's kind of a more complicated structure. So actually this kind of method cannot represent the complicated graph structure. And of course, SMILEs cannot effectively reflect the complex relationship between atoms of the drug structure. And the overall performance is not satisfactory. Is not satisfied. So we can see that only a small part of functional groups are changed in a chemical reaction. So we can localize some change of the graph. And so we for the motivation, the second motivation is that the reaction mechanism are often depicted using electron arrow pathing diagram, where each arrow corresponds to a bond to be generated or to move. So we can remove a bond, or we can add a bond. Then we have a different structure, and we can check if this kind of action is reasonable or not. So we propose a new model, which is called G2G. This is a novel template-free method, and it represents its molecules as a molecular graph. And it formulates Rachel synthesis prediction as a graph-to-graph translation. So we can compose a new drug structure from some small sub structures, which is represented as a graph in our paper or in our research. The whole framework is composed of two stages. One is reaction center identification, and then the second one is graph translation. So first of all, we need to identify the reaction center, which is very important. So the overview structure of a G2GS model is in this way. So first of all, we have a reaction center identification, and then we break the product to symptoms to smaller parts. And then we have some variational graph translation. So we just as a language translation, we translate from some graph to other maybe smaller graphs because this graph is the product graph is relatively larger one, and then we need some smaller one, and we have a reaction among these smaller ones, and then we can compose the product. So for the reaction center identification, we can see that an atom pair IJ is a reaction center. If there is a bond between atom I and the atom J in product, so they have some connection. And there is no bond between atom I and atom J in reactants. For this G2G reaction center identification, to identify the bond between with high reactivity, our model first embeds the target molecule into a low dimension space. And especially we employ a graph neural network to calculate the node embedding and the graph embeddings of the target molecules. Then we estimate the reactivity of each bond based on its age embedding. The bond with a high is the reactivity score is selected as the reaction center. Then we break the corresponding bond. In this way, the target molecule is split into multiple symptoms, which can be later translated into final reactants. Through reaction center identification module, we reduce one-to-many graph translation task into multiple one-to-one graph translation tasks. That's simplify the problem. Then we have the graph translation. The goal of graph translation is to translate its incomplete symptom to the final reactant. And the method is conditional graph generation. It's treated as a mark for decision process. And also we consider the diversity. We incorporate a latent code Z to capture uncertainty. So and we can see how graph translation is done in following illustration. Our graph translation module has 4 actions. Given the current symptom, it first select a node to focus on. See, we select a carbon atom here. First, we select carbon. This one, and then we select a second node to focus on, and then we select the an edge type. After 2 nodes are selected, the model select the edge type for edge between these 2 nodes. Note that if the second node is an isolated node, it corresponds to adding a new node to current symptom. And finally, it's termination prediction. Our module predicts whether the graph translation is done or not. If it needs to be terminated, the current symptom is regarded as the final reactant. If it does not, the module will select another node and repeat this procedure. The experiments results show that G2GS archives state-of-the-art results comparing to the baselines. And also we have some visualization to show how to do this. How does the G2GS model works? To give a deeper insight into our model, we also we show this visualization part, and the figure in the left shows some successful prediction made by G2GS, and the template entailed by these reactions are summarized below. So this the bottom one. The figure in the right represents a case where none of the predictions match the ground truth. However, this does not mean our model fails to predict a synthesis route for the target molecule, as a molecule can be synthesized in multiple ways. To further illustrate this point, we employ a reaction prediction model to predict the product based on the reaction generated by our model, which is shown in the bottom of the right figure. We also found 2 similar papers published also in 2020. The first one is done is published in XML graph representative learning workshop, and the second one is accepted by Neuro IPS. One is done by MIT, and the other one is done by that's Tencent group in China. And we can see that both papers they have fewer citations compared with our two papers. The first paper, the graph AF model, published in ICLEA 2020, we have 19 citations right now, and the second one in XML we have 6 citations, and also and also at least the two fundamental models which is proposed, which are proposed by our group. The first one is line, published at www 2015, and the second one is large width, which was published in www 2016. And that's all for today. Thank you. And any questions?